is Brian Nakamura, the co-organizer of this seminar, who will speak about an overview of the Černý Conjecture.
So I'll be shooting just kind of for a very general overview of the conjecture. So I'm going to start off with just going over some standard theoretical computer science definitions and notation. And so to start off, I'm looking at deterministic finite automaton. And so they're basically ordered triples where I have a set of states, Q, some input alphabet, sigma, and then delta, which is a transition function, basically showing how the letters in the alphabet of sigma act on the states Q. And just for notational convenience, oftentimes when I'm referring to a delta QA, I may just shorthand it to Q dot A. Right? So the letter A applied to state Q. And so just an example. So here's an automaton. So the state set here is 1, 2, 3, the vertices. The input alphabet, sigma, consists of A and B. So they're the labels on the directed edges. And the transition function itself would be, from state 1, if I traversed along letter A, and I'd end up in state 2. Likewise, from state 1, if I moved along letter B, I'd end up in state 2. And equivalently, that's just the shorthand notation on the right side. Likewise, from 2, if I moved along A, back to 2, and from 2, if I moved along B, end up in 3, and so on. From 3 along A is back to 3, and along B would be 1. So now, I'm going to refer to a sequence of letters as a word, natural name. And so, each of the SIs are a letter from sigma, and I'll also denote this as the length of the word, the absolute value of W as the length. And now the transition function, you can extend it in 2 natural ways. The first is if I start off with a state Q and I want to apply the word W to it, essentially I apply the first letter first, then the second letter of the word, then the third letter, and so on. So basically W represents a unique path to travel along starting at state Q. And also, if I have a subset of Q, so I have some subset of the states, then I can also imagine the word W being applied to the whole subset. So basically, each state in this subset, I apply the word to each state. And also here's some more shorthand, just because writing the deltas over and over gets kind of cumbersome. So when I apply the word W, when I apply the word W to Q, I may just write it as Q dot W. And when I apply the word W to the set S, I may just write it as SW. And here I also drop the period because usually, sets I'll use a capital, so.
Should we give an example to this?
Yeah, so that's next.
Okay.
Yep. So, as an example, so again, this is the same one. So I have, again, state set 1, 2, 1, 2, 3. And I have alphabet A and B. And so if my word was AABB, so if I apply this word to state 1, then starting at state 1, I follow AABB. So I move A here. When I hit the second A, I stay put. Right? The third, then the B takes me here, and then the B takes me back to 1. And if I start at state 2 and I go along AABB, the first and the second A keep me still at 2. Then the B brings me to 3. Then the last B brings me to 1. If I were to start at state 3 and follow along AABB, So the A's keep me here. So A, then the B brings me here, and then the last B brings me to 2. And so in the prior notation with the sets, if I apply the word to all the states Q, then the resulting, in a sense, it's almost the resulting image I get is states 1 and 2. And now here I'll also point out, so one way you can interpret this is, imagining that for each state you're traversing along this word. A slightly better for what I'll be doing later, a slightly better interpretation would be to imagine you have a set and then applying each letter one at a time to the whole set. So if I start off with everything Q, that's all 3 states. So then I'm going to apply the first letter A to all 3 of these states simultaneously. So the first state 1 shifts to 2. The state that was at 2 stays put, and the state at 3 stays put. And then I apply A again, and so 2 stays put, 3 stays put here. Then I apply the letter B, and this state transitions up here, and this state transitions here. And then I apply B one more time, and then this state moves here, this state moves here. So I have 1 and 2. And so this will be kind of a more natural way to kind of look at this. Next, I'll define a word. I'll call a word a reset word if when I apply that word to any state I want, it takes me to one particular state. So regardless of the starting state, it will send me to one particular known state. Right? So the same word. So in a sense, the reset word kind of resets my position in the automata. Right? And equivalently, I can also view this reset condition as if the QW just has only one state. And this is what we'll be dealing with for most of the rest of the talk. And then an automata is called synchronizing if it has a reset word. So this is a very, very special property to be able to reset it with one specific word. So if it happens to have, if there is a reset word, then the automata will be called synchronizing. So kind of a very specific class of automata. So back to this previous example. So again, I have states 1, 2, 3, and the letters A, B. And so now my claim is that the word ABBA is a reset word. So if I start at state 1 and I apply the word ABBA, I move from 1 to 2, B takes me to 3, B takes me to 1, and then A takes me back to 2. Starting at state 2, if I apply the word ABBA, the first letter keeps me put, the B brings me to 3, the next B brings me to 1, and the last A brings me back to 2. And if I start at state 3, the A keeps me put, the B brings me here, the next B brings me here, then the last A keeps me put again. Right? So regardless of the state I start at, this word will bring me to state 2. So it's a way of, in a sense, if you lost track of what state you're at, it's an input that will reset your position to one particular state that you know. And likewise, so in this notation, right, if I apply the word ABBA to all the states simultaneously, then it'll just be the singleton set too. So again, if I view this as the word being applied to sort of subsets, one letter at a time, so again, I start off with 1, 2, 3. When I apply the letter A, this state transitions over here, this state stays put, this one stays put, so I have 2 and 3. When I apply the B, this one moves up here, this one moves here, so I have these 2. When I apply the B again, this one shifts here, this one shifts here, so I have these 2. And then when I apply the last A, this one moves over here, and then this one stays put. So basically the same thing, but that's sort of, I guess, perspective helps out in some later analysis we do. So now the conjecture itself is a Černý conjecture. So it was it's written to be conjectured in 1964. The conjecture was technically not fully formulated to maybe a few years later, but it's that if you have an n-state automaton that's synchronizing, then the shortest reset word will have a length of at most n-1 squared. Right. And so note here, so let me I can just jump over here. Right? So this is a previous one. So here I have, technically my input alphabet is only 2 letters. And so here technically it doesn't matter how many letters I have in my alphabet. So it can have more than 2. Right? The alphabet can be more than 2 letters, but as long as it's synchronizing, then the length will be no more than that length. Right? So it only depends on the number of states. And so in a sense, though, having more letters, you would expect it to actually shrink the shortest, because then if you have more letters, you just have more options to shift around. But, all right. And then also a comment, so if the conjecture is true.
It's only intuitively. There's no theorem that says if you can prove it, for 2 you can prove it.
It's only intuitively, so there's no there's no sort of reduction where
because consider about that we have more letters. It's before it was possible to be synchronized. Adding more letters will make it possible to be synchronizing, but make the length longer.
So there is a.
So there's no theorem that says that it's sufficient to prove it for 2 letters.
The problem would be if it, I guess, it has three letters, words, options. Then if you take one of them away, we don't have synchronizing anymore.
Right. So that you would expect.
But
there's no theorem that says that. Right. Yeah. So there's no theorem that says you only have to worry about just 2 letters or 3 letters or so. Yep. And also so here so if the conjecture is true, then the bound itself would be tight. So there's an infinite family of synchronizing automaton where for each state, for each n, it's synchronizing and the minimum is exactly n-1 squared. And so this was also shown by Černý. So this is just a construction. So this is actually basically a generalization of this specific one here. But so here this has n states. The minimum reset word for this would be this word here, where basically this means you have A followed by n-1 b's, and then that word is repeated n-2 times. Then you append one more final A. And so that's exactly length n-1 squared. And also, in addition to this, there is also a particular example of where n is 5, and it actually has 3 letters, but it still hits the bound for the minimum. So, and now, so the current status. So let me just mention. So. Černý conjecture. So the min reset word W has length no more than n-1 squared. Right, so it's on the order of n squared. So the best recent sort of global bounds, in a sense, and here I put recent in quotes, is let's see. So first in 1983, for any synchronizing automaton, it was shown that you can always, the minimum reset word will be no more than this n cubed minus n over 6. So initially, when Černý conjectured it, he had some 2 to the n, some exponential length, and then shortly thereafter, it was brought down to an n cubed bound. And then over the years leading up to 1983, it was kind of whittled away, still n cubed. And then it kind of hit this point. And then this was sort of the best result for a long time, actually up until earlier this year. And then I believe
But
around...
this is because Frankel, really, huh?
Part of the bound is, but it's generally attributed to Pin. So Pin showed the general kind of the, I guess what I'll mention later, but the greedy algorithm portion improved, he basically reduced it down to a combinatorial problem, and then Pin finally solved the combinatorial, Frankel solved the combinatorial problem. So it's generally, I think, attributed to Pin. And then earlier this year, the bound was improved. It's still n cubed. And actually, if you look at the coefficient of n cubed, it would be 7 over 48. 1/6 is 8 over 48. So it was basically, the coefficient was lowered by 1 over 48 after 28 years. And of course, the conjecture itself is n squared. And so I'll kind of sketch the rough outline of how this comes about. And also, in particular, for specific classes of synchronizing automata, the conjecture has also been shown to hold. So if the automata is synchronizing, but also has some additional properties. So I'll also mention that a little bit later. But so first, jump back. So this bound here, the initial n cubed bound, basically is based off of, if you were to search for the minimum reset word via a greedy algorithm, and it's basically analyzing sort of the worst case for this greedy algorithm. So for the greedy algorithm, I start off with a set of states Q and alphabet sigma. And for the algorithm, so I'm going to initialize, I'm going to basically construct my reset word W. And I'm going to initialize it first as sort of just an empty word. And then I'm going to start off, and the idea is that I eventually want to find a W where if I apply it to Q, I'm left with one singleton set. But I'm going to keep appending, I'm going to build up this W to keep shrinking the size of the set I would get until I would get a singleton. And so the algorithm is fairly simple. So anytime the PI is not a singleton yet, then find a minimum length word so that if I applied it to the PI, it would decrease the number of states in that collection. Right? And then basically I update my PI and I update my W. So let me. So the idea is that I start off with, say, my set of states Q, and I think of this as I find a word so that this will be my P1. When I apply this word W1, the number of states decreases. So P1 is equal to QW1. And then from here, I want to find a word so that when I apply this word here, then this also decreases, the number of states also decreases in size. So P2 would be P1 W2. So P2 would basically be Q, and then I apply the word W1 first, and then I apply the word W2 to it. And I keep doing this until basically I have some word WK that takes me to some sort of a singleton set, PK, where PK only has one state left. And so, and then And then in the end, W, which is sort of the concatenation of all these words I found along the way, would be a reset word. So W, W1, W2, all the way to WK, right, would reset. It would basically take me from Q to P1 to P2 all the way to PK, which is a singleton set. And let's see. And so here, so the while loop itself, the idea is that each time I want to find some minimum word to kind of pack on to my kind of running word that'll sort of reduce the number of states I currently have. And so in the worst case, the while loop, so in the worst case, I may, each step I may only reduce the number of states I have down by 1. And so in the worst case, I may end up repeating this process n-1 times. I start off with n states and take it down to 1. Right, so k, right, in the worst case. And so basically, so if I want to find an upper bound for this reset word, then it's enough to find an upper bound for each sort of, right, each of these WIs, sort of each portion. And so, so again, so the while loop from before is executed at most n-1 times. Right? Now when I bound each of these sort of subwords, and so this is where Frankel comes in. So for each I, he found a bound. So Pin had shown that this you can sort of analyze it in this way, and Pin had conjectured that you can produce this bound for the WIs. Then I think at a conference he kind of presented it, and Frankel was in attendance, and so he was able to kind of solve it shortly thereafter. But yeah, so the problem itself essentially was sort of turned into like an extremal set theory problem. And right, so yeah, I think it's, so there's this, and of course then you sum over everything, and then your reset word W will be no more than the n cubed, sorry, n cubed bound.
Sorry, maybe you said this before and I missed it. So is there a sufficient condition for being synchronizing?
Not really. So that's actually one of the hard parts of the conjecture as well.
I see.
Because if you have sort of the directed graph, depending on how you put these labels, even if you change the labels around on the directed graph, in some cases you may get something that's synchronizing, and in some cases you may get something that's not synchronizing.
Okay.
And actually that itself was actually an open problem for a while. That one of the previous people I mentioned, Trotman, had solved, called the road coloring conjecture, was if you started off with a digraph that was strongly connected, is it possible to add labels so that it becomes synchronizing? And so, right, so structurally, kind of the structure itself isn't enough to know whether it's synchronizing or not. It depends on where the labels, like each of the A and B's are, or yeah. So yeah, I guess that answer your.
Yes.
Yeah. Okay. There's that. And check. So continue. And so now from there, so Trotman actually improved the bound earlier this year. But so he started off with this result. And so in his paper, technically, this was listed as a lemma. I've upgraded it to a theorem. But basically what this says is, so as of now, the previous bound for W was found by bounding each of these, each specific WI. And the bound itself is not, it's not a very efficient bound. So actually, if I jump back here, for example, right, in the case that I is n minus 1, so in the case that I is n minus 1, then this bound tells you that this very last step, right, just this step right here, is no more than n choose 2. But that's already an n squared upper bound by itself. So, and for the conjecture, right, I mean, we have this n squared bound. So, actually, yeah, as you move further along, the bound kind of gets worse and worse. Now the issue is sort of the set theoretic problem that this was converted to get that bound. That set theoretic problem, for that problem, this bound is actually tight. And so from that perspective, the bound can't be improved. So that. And so what Flatmans showed was that you could do a little better. Basically what he says is that up until the halfway point, so if this was, let's say, this right here was basically roughly the halfway point here. So up until the halfway point, you can find a word here of length at most sort of a k squared. So you can find a word of this length that'll get you to this state, this position. You can find a word of length 1 squared. You can find a word that'll get you from here to here of length 2 squared. You can find a word from here to here that'll get you to 3 squared. I mean, ideally, it would be nice if you can do that all the way, and that'll get you to n minus 1 squared. But actually, that's been shown to not be true. But he showed that you can actually go halfway. So it's roughly kind of this n over 2 squared. And then that actually improves the first half of the approximation. And then the rest of the way, he still uses the greedy algorithm to approximate the rest of how long the word will be. And so, based off of that, so he literally just took this bound here and then just kept summing up using the old bound. And then that gets you the improvement of 1 over 48 for the coefficient. So, yep.
Well, why couldn't he like apply that result? He gets it and then he cuts it in half using n over 2 squared steps, and then he cuts the problem in half again using n over 2 squared steps, and then that would give him like something like an n. Well, I don't know what that'd be. Something.
Well, so the n squared, so this k squared is actually the best you can do. Up until halfway.
He thinks of another problem after that. Like you cut down the state from q to like half as big, and it takes you n squared over 4 to get there. And then you start with this new state, and then you cut that in half.
Yeah, so it doesn't quite work out so cleanly in terms of like how the proof is constructed. And also the result itself, yeah, so the k squared is actually the best you can do. For a while, there was actually a generalized conjecture, the Czerny's conjecture, saying that basically that for every step, for every stage, you can get from the starting position to the k stage in k squared steps, or k squared word of length k squared, called the deficiency conjecture. And so in this case, if you're allowed to do that all the way, then of course, if k is n minus 1, then the generalized conjecture would say you have a word of n minus 1 squared. But yes, but there was a counterexample found to that, and so the counterexample happens just beyond the halfway point. So for a 6-state automaton, kind of at the 4th step, it breaks, and instead of a length 16 word, you're forced to have a length 17 word sort of thing. So now, maybe just to kind of elaborate a little bit more, just kind of on the difficulties of the conjecture. So first off,